Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So today we're continuing with our series on writing a ray tracer in C++ using as far as possible only the standard libraries along with the SDL2 library so that we can display results in a window. In particular, in this episode we're continuing with our mini-series looking at improving the performance of the ray tracer that we've written so far. So if you remember from the previous episode, we were able to reduce the runtime for rendering our simple test scene from about 34 seconds down to about 12, which was pretty good. What we're going to look at in this episode is how we can go about reducing that even further. Some simple changes that we can make to better implement the new vector classes that we created in the previous episode, and we're going to look at creating a new matrix class to make matrices faster as well. Hopefully that will be of interest. Before we dive in, that just leaves me to say, as I always do, that if you like this video, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so that you don't miss any future videos. Thank you very much. Right, without much further ado, let's jump into it, and let's look at how we can improve the performance of our ray tracer even further. To begin with, I'm here at the terminal window, and I thought we could just start by taking a look at where we were at the end of the episode last week. So I just want to compile that. I'm now compiling make using make with the -j switch that makes it run in parallel. Thank you ever so much to the person who commented about that. But thank you for that, that's really useful. Let's run QBRay and let's just have a look. So this is the code that we had at the end of the episode last week. And there we go, 11.8 seconds or about 12 seconds to render this scene. And as you can see, if you're new to the series, this is a fairly complicated test scene. There's quite a lot going on. We've got normal mapping, texture mapping, various different shapes. The torus or donut shape is made using ray marching, and we've got reflections, rough reflections on the walls, smooth reflections on the tiled floor. So it's a fairly complicated scene, and I think, about 12 seconds is not bad. But we can go a lot faster. Okay, so I just want to show how much faster we're going to be able to go by the end of this episode. So this is the new version of the code. I'm just going to compile that. It shouldn't take too long. Okay, and let's run QBRay again. Bring the window over. You can see immediately that is a lot faster. And so there we go, 3.6 seconds to render the same test image, which I think is really quite an impressive improvement. So remember, at the start of this little mini-series on performance, rendering this scene was taking 85 seconds. And we haven't really made any huge changes to our code base. Really, the biggest change that we've made was changing the QBVector class to use memory from the stack rather than memory from the heap. And you can see by then better implementing those changes, which I'm going to go on to look at in a moment, we can actually bring our rendering time down to just 3.6 seconds for the same scene, which I think that is actually pretty extraordinary. So before we dive into all of the changes that I've made to do that, I want to talk a little bit about the new matrix classes that I've created. So let's have a look at that. Okay, so one of the challenges that I faced with making this go a lot faster was to create a new matrix class in the same way that I created new vector classes in the previous episode. So the idea being to remove the reliance on heap memory and rely more on memory from the stack, which, as we know, is faster. So the existing qbmatrix.h library that we've been using from the linear algebra library that I developed in the previous series uses memory from the heap, and that's really useful in that context because we might want to create a matrix of any size. Okay, we have no idea. The linear algebra library is designed to be a generic, potentially useful with huge matrices and vectors if you're using it to solve systems of linear equations or principal component analysis or whatever. However, in the case of our ray tracer, we really don't need that. We are, in all likelihood, only ever going to need 3x3 or 4x4 matrices. So that leads to the possibility that we can use memory from the stack because we know exactly how big they're going to be. So we don't need to use dynamic arrays or anything like that, which is, of course, when we need to use heap memory. And that will make things faster. Okay, so what we're going to do is we're going to create two new classes called QBmatrix33 and QBmatrix44. We're using templates, so they're of type T. T can be double or single, precision, whatever you need. The purpose of these is to handle the 3x3 and the 4x4 matrices respectively, and nearly all of the code for the matrix arithmetic is going to remain the same as we had for the original QB matrix class. Now, I'm not going to talk about all of that in detail because it's covered in the episode on creating the linear algebra library. I'll put links to that in the description below. But we do need to consider changing the code to compute the inverse of the matrix. Okay, so now previously, for calculating the inverse, because we were dealing with a situation where we could have matrices of any size, potentially really large, I implemented computing the matrix inverse using Gauss-Jordan elimination, which is a perfectly good way of doing it if, you know, you're dealing with really large things. However, for smaller and in particular fixed size matrices, there is a simpler way. We can actually do it analytically using this equation here. So this shows us that the inverse of the matrix A to the minus 1, is equal to 1 over the determinant of A multiplied by the transpose of the cofactor matrix, or the adjunct or adjoint matrix, depending what you want to call it. Okay, so that's pretty simple. What we need to do is, of course, be able to calculate the cofactor matrix, or the adjunct matrix C, and given a matrix A with elements A11 through to A33, then the matrix C is given by what you can see here. So what we have is the first element of C is simply plus the determinant of A22, A23, A32, and A33. So this is a sub-matrix, so, or a cofactor matrix of A, and it corresponds to this. So we're replacing the element A11 with this submatrix here, okay? And then we have minus A21, A23, A31, A33, and so on. You can see how that comes together to create the matrix of the cofactors, okay? So then we just need to know how to calculate the 2x2 matrix determinant, which is simply given by this. It's simply AD minus B, A times D minus B times C. Okay, that's really straightforward, and therefore we can compute C, we can transpose that to get C transpose, and then in the 3x3 case, it means we can simply write code to do that. We don't need to do anything complicated, and to compute each element of the cofactor matrix, and that leaves us only to compute the determinant, of the original 3x3 matrix. And that, again, we can write that down. It's a fairly simple formula. It's simply, for a matrix A, B, C, D, E, F, G, H, I, we simply have plus A times the determinant of E, F, H, I minus B times the determinant of D, F, G, I plus C times the determinant of D, E, G, H. Okay? And that's quite straightforward, and we can write that down in this format here. When we come to see that in the C++ code, it will look a little bit different, but that's simply because I've expanded out these multiplications. We can put all that together in code, and we can compute the inverse of a 3x3 matrix. Quite straightforward. Okay, now for the 4x4 case, a little bit more complicated, but not much, so bear with me. We use the same formula, that A to the minus 1 is 1 over the determinant of A multiplied by the transpose of the cofactor matrix, but now we have to compute a 4x4 matrix determinant and cofactor matrix. So for the determinant, we have that the determinant is simply equal to A1 multiplied by the determinant of the first submatrix, which we can see there. So I've highlighted the submatrices in yellow. And then we have minus A2 multiplied by the determinant of the second submatrix, plus A3 times the determinant of the third submatrix, and so on. And I think you can see from that how the submatrices are formed. We ignore the row and column of the element in question, and then take the remaining elements, put those together into one matrix, okay? And then we simply have to compute the determinant of that, okay? And we've already seen how to compute the 3x3 determinant, so using that, we can see how we can easily compute the 4x4 determinant. For the 4x4 cofactor matrix, we just need to compute the determinant of each of the 3x3 submatrices, okay? So we have our 4x4 matrix there. For the first element of the cofactor matrix, we would compute the determinant of the elements you see in yellow. For that one, the elements in yellow. For C3, we would the elements in yellow again, and for D4, we would do that. And we do that for all of the elements, not just the diagonal ones. I just showed the diagonal ones there for illustrative purposes of illustration. So in the 4x4 case, we need a function to extract the submatrix for any given element, and we can then compute the determinant of each of those submatrices to get the cofactor matrix, and we can also use it to compute the determinant of the original 4x4 matrix. And then we can use the equation from the start to compute the inverse, and that's what we need to do. Okay, so let's take a look at how we'd implement that in code. So I've created two new files in the linear algebra library called QBMatrix33 and QBMatrix44. Let's have a look at the 3x3 case, or QBMatrix33 first. So this is our code here. Now, as I said at the beginning, I'm not going to go over all of the details of matrix arithmetic. I'm just going to talk about the specific changes. If you want to know more about really how it works, go back and have a look at the relevant episodes in the linear algebra library series, which I think is quite interesting. I quite like, from a sort of geeky perspective, rather like linear algebra. I think it's kind of cool. But anyway, so we have our various constructors. Obviously, we can construct a default matrix 3x3 matrix. We can construct it from another 3x3 matrix, or we can construct it from an STD vector containing the input data. We do have a destructor. We don't really use it for anything. We have a function to set it to our identity, so we can create a default matrix and then set it to identity to create the identity matrix, which you might need. We have element access methods, which I've preserved to maintain compatibility. We have our function to compute the inverse. Note the inverse returns true or false. Not every matrix, even square 3x3 matrices, not every one can be inverted, so this will return false in the event that you pass a matrix that can't be inverted. Talk about that in a moment. We have a function to transpose our matrix, we have a function to compute the determinant, and then we overload the various operators, the equality operator, and we have a separate function to compare with a specified tolerance, because if we're using double precision, we might not want to compare exact equality with numbers. We can accept a certain tolerance for that. I talked about that in the linear algebra library series. We overload the assignment operator as well, and then we have our overloaded arithmetic operators, plus, minus, and multiply, and we have a function declared a friend, and this is for multiplying QB by QB matrix 33, sorry, by QB vector 3, okay, which is the only case that we need to overload for vectors and QB matrix 33. A private function sub to ind simply converts a row column to a linear index into our linear array. We have a function to compute the cofactor determinant, simply returns the determinant of the 2x2 matrix, and a close enough function simply to compare whether input 1 is close enough to input 2. And then we have our private. So previously we declared a pointer for m_matrix data because we were allocating memory from the heap. What we're doing now is allocating memory from the stack, so we simply declare this as a fixed array. We could do that because we know exactly what size it has to be. So n matrix data is simply now a 9-element array of type T, and we fix num rows, num cols, and num elements accordingly. Okay, so constructor, destructor, we don't really need to talk about anything there, I don't think. We have the configuration functions. This is set to identity. This function will just loop through and will build the identity matrix, populating the 1s and 0s accordingly. So we have 1s just along the diagonal. We have our element functions, get element. This shows example of use of the sub to ind function, which accepts row column, calculates a linear index from using sub to ind, and then uses linear index to index into n matrix data. Okay, that's how it works. And then we have set element, obviously get num rows, get num cols, compare. We don't need to talk about that really. And then we have the matrix arithmetic. As I said, I'm not going to talk about that. The one I do want to talk about is this one, matrix times QB vector 3. This accepts as input a reference for the matrix and a reference for the vector. We allocate a QB vector 3 to store the result, and then we're simply going to loop over all of the rows, and then we calculate the cumulative sum there as we go, and then store that in the relevant element of our output vector, and we return the result. Dead simple. Okay, so we have scalar times matrix, matrix times scalar, matrix times matrix, not going to talk about that. It's discussed in the linear algebra library series. We overload the equality operator as well, which uses the close enough function rather than computing exact equality. Okay, then we have the assignment operator, simply copies it's one to the other. We have a function to transpose. Okay, that's pretty straightforward. Set element ji, get element ij, pretty easy. Okay, and then we have the function to actually compute the inverse. So this is the function that implements what we were just talking about. The first thing we do is we compute the adjugate matrix, or the cofactor matrix, or the adjoint matrix. It seems to be called a number of different things. And this will look a little bit different to the equations that we had, but as I said, it's because the brackets have been expanded out. And you can simply see this is calling the cofactor determinant method, and cofactor determinant is simply a function that computes the determinant of a 2 by 2 matrix, and we pass to it the 4 elements of that matrix. Okay, and you can see quite easily, I think, how that works to build it. And we build up the adjugate matrix, and then we transpose it, and then to compute the inverse, we compute the determinant of our existing matrix. So we're just calling the determinant function that will return the determinant, okay, of type T. A determinant is a single scalar value of type T. We check if it's close enough to 0, and in the event that it is, we return false. Now, the reason we do that is because if the determinant is equal to or close to 0, then it's very likely that we have a matrix that cannot be inverted. Because we're doing 1 over the determinant, if the determinant was 0, 1 over 0 is undefined. So that would make no sense. So we have to make sure that we catch that and we return false. Assuming that's not the case, then we actually compute the result as simply 1 over the determinant multiplied by the transpose of the adjugate matrix, and that gives us our result that we store in another QB matrix 33 instance, and we store it in place. So we then loop through and we simply copy from result.m matrix data into m matrix data, and we return true. And that's it. It's actually quite straightforward, especially compared to the Gauss-Jordan elimination algorithm that we had for dealing with generic matrices. But there we are. That will give us the inverse of the 3 by 3 matrix. And we also have the function, of course, to compute the determinant. We're using that here as part of the inverse. And yeah, that's pretty straightforward. That's simply the maths from the slide that we saw, again with the brackets expanded out, so quite straightforward. A private function sub to in simply converts row col into a linear index. Okay, really straightforward. We could replace mn cols and mn rows with the fixed quantities because we know, but yeah, never mind. I copied that from the generic code. I think it's okay. We have a function to compute the determinant of a 2 by 2 cofactor matrix, simply element 1 times element 4 minus element 2 times element 3. That's really basic. And we have our close enough function, simply returns the absolute value of f1 minus f2 less than 1 times 10 to the minus 9. Okay. That's it for QB matrix 33. QB matrix 44 is basically the same, but let's just have a quick look at it. Okay, so this is QB matrix 44. Everything is the same really except for the name. We do have some additional things. So we have a new function here called find submatrix that we didn't have before, and of course multiplying a matrix by a vector, we are only dealing now with the QB vector 4 case because there would be no point doing anything else. And of course we have 16 elements of our matrix data. We're 4 by 4 and 16 elements. Okay, so we don't need to talk about constructor, destructor, element functions. Those are all the same. Overloaded operators, basically all the same. What is of interest is really when we come down to the inverse. Before we talk about that, let's just have a look at the private function. So we have find submatrix. Okay, so for a specified row and column index, this will return a submatrix, which is important to note is a QB matrix 33. Okay, so the submatrices of a 4 by 4 matrix are obviously going to be 3 by 3. We loop over the elements of the existing matrix and copy to the submatrix as required. So we loop over every one. If I loops from 0 to mn rows, j from 0 to mn cols. If I is not equal to row num, j is not equal to col num, then we copy it. We're simply using count as our index, which we then increment. That's pretty straightforward. I think if you work that out on a piece of paper, you'll see how that's working. Okay, close enough. Sub to in, those are the same as we had before. Our determinant function, this is now slightly different. So we're looping over the 4 columns. We're taking just for row 0, just for the first row, and all 4 columns. For each one, we are going to find the submatrix for the corresponding row column. Row is always 0, so but that doesn't matter. And that will give us a QB matrix 33. And we then compute the determinant of that using submatrix.determinant. And then we have simply a cumulative sum plus equals this business here multiplied by our current element multiplied by submatrix determinant. Now this business here, static cast at t of sine initially starts at 1. After this it's multiply equaled by, so that's the same as sine equals sine multiplied by -1. So it'll go from 1 to -1 the next time round. That will be -1, and then it will be +1. -1 plus 1 minus 1 plus 1, and that gives us exactly the pattern that we need, okay, as you saw from the slides at the beginning, right? And then that simply return cumulative sum, and that is our determinant. Computing the matrix is the inverse, of the matrix is pretty much the same. We loop over all of the rows and all of the columns to compute the adjunct or adjunct or cofactor matrix, okay, which is a type QB matrix 44. Of course, it's a 4x4. First thing we do inside that loop, inside the two loops, is we compute the submatrix of the QB matrix 33, a 3x3 submatrix, okay, using find submatrix. We find its determinant, and we set the element of the adjunct matrix at row col to be equal to sine multiplied by the submatrix determinant. And then exactly as before, sine starts out at 1. And then we multiply it by -1 each time we come through this, so it goes 1, -1, 1, -1, just as before. The difference is that we now have a row sign in order to make sure things are right. That starts out at 1. At the end of our loop through all of the columns, we multiply row sign by -1, so it'll go 1, -1, 1, -1 for each row as we go through, okay, and you can see how that's going to give the right result. That gives us the adjunct matrix, which we then transpose to give adj t as before, and we compute the determinant of our 4x4 matrix using the function we just looked at. If that's close enough to 0, we return false, just as before, because that would indicate a matrix we can't compute the inverse for. And then we compute the result as simply 1 over the determinant multiplied by adj t, and we store in place exactly as before. Okay, so that's quite a lot to go over, but I felt it was important just to describe the changes to the new QB matrix 33 and QB matrix 44 classes compared to the generic QB matrix 2 class that we were working on before. Okay, so I just wanted to quickly talk about some of the other changes that I've made. I went through the process of using the profiler, as we saw in the last episode, making changes and then going back and looking at the profiler again. And it's an iterative process. I'm not going to go through and show all of that now. I don't think that would be particularly exciting. What I want to do is really just talk about the changes that I've made. I'm not going to talk about all of them, but it'll be enough to show an example of all of the changes I've made. So starting in ray.hpp, the header file for the ray class, I've modified this to make better use of the new QB vector 3 class. So previously we were instantiating our vectors. We had to pass to them an std vector type double with an array in it, and so that required instantiating not only the QB vector but also the std vector as well, which is silly. So the new QB vector 3 class allows you to instantiate it by simply passing 3 numbers of 3 doubles, so we can simply define m.1 and m.2 for our default situation and MLAB using that. Okay, that's pretty straightforward. That's everything we changed there. So in gtfm.cpp, so this is a class that implements the geometric transforms, hence GTFM, geometric transform, and this is going to use the new matrix classes. So in the header file, actually let's have a look at that. Okay, so GTFM HPP first. This uses the new matrix classes. So previously we had QB matrix 2 type double, m underscore forward transform, 4x4, backward transform 4x4, and 3x3 matrix for the linear transform. And now we simply declare those as QB matrix 44 and QB matrix 33 as required for those 3. That's pretty much everything here. Set transform is a bit different as well. And yeah, the constructors a little bit, we've replaced instances there of QB matrix 2 with QB matrix 44. Okay, that's all pretty straightforward. Let's have a look at the CPP file. Okay, GTFM, sorry, .cpp. So that's all the same. We initialize to identity matrices, and we accept as input QB vector 3s for translation, rotation, and scale. I think we talked about that before. Construct from a pair of matrices. Now we have QB matrix 44 as the input. Okay, so we know they're going to be 4x4, so we no longer need this code here to verify that. We can simply copy them into m forward TFM and m back TFM, and then extract the linear transform as before. We have our function to set the transform, which accepts 3 vectors for describing translation, rotation, and scale. We initialize a translation rate matrix, 3 rotation matrices, and a scale matrix, all of type QB matrix 44. We set them all to identity, and then we go through and set the elements accordingly. And then we combine those together to give the forward transform, which we then copy into the backwards transform and inverse it. This is why we need the functions to invert matrices. Set transform, that hasn't really changed except for, it's QB matrix 44 now. And that's about it. That's pretty much everything. Apart from apply here, where we have an input vector and a dir flag. Before, what we had to do is we initialize temp data to be because we're using homogeneous coordinates for our geometric transforms, we have to convert our 3-element vector into a 4-element vector, with the last element, the 4th element, simply being equal to 1. And we did that this way before by instantiating an std vector to give temp data and then creating temp vector. We don't need to do that now. We can simply create temp vector as a type of QB vector 4, and we simply pass input vector element 0, input vector element 1, input vector element 2, and 1 as the last element. Okay, so that's better. This is the sort of change that actually makes really quite a significant difference to the performance, I found. And we do the same when we reformat the output. The output should be a 3-element vector, so we have to do the opposite of that operation. Really we're only interested in the first 3 elements of the result. Okay. And that's about it. Everything else here for combining transforms, that hasn't changed except for use of QB matrix 44. That's about it. Okay. So that's it for GTFM. Okay, object plane.cpp, so this is an example of the changes to the actual object classes themselves. Okay, that's a little bit careless. That's still instantiating those using std vectors. We can change that. I'm not going to do that now because that's in the constructor. It doesn't affect actual runtime performance once the scene has been created. But even so, we should do it properly using the new way. I will change that later. We come down into test intersection, and I've made some changes here. So before, we were making a copy of the MLAB vector from BCK ray. So BCK ray is the result of applying the transform matrix to the cast ray. Okay, it's an instance of the ray class, and so it has the start point, the end point, and the difference between them stored. Okay, so rather than doing that, which involved instantiating another vector, I've simply commented that out for now. And wherever I referred to k, which was of course this result here, which was then normalized, we didn't need that normalization. So now we can use BCK ray m_lab dot get element 2. So I've replaced every instance of k with BCK ray. So we directly use BCK ray, and that just saves having to do this extra allocation. And this is the test intersection function. It's going to get called a lot. So anything that we do to improve its performance is going to be quite significant. And then basically the same everywhere here, all the maths. Wherever there was a k, I've replaced it with BCK ray dot m_lab. That's exactly the same thing, every instance of k. So here t times k is now t times BCK ray dot m_lab. I think you can see what's going on. Compute the local normal, we have all that code there. I've commented that out, replace that with instantiate the new QB vector. We simply use the apply norm function from the GTFM class to give that. And compute UV. And at the moment, yes, we are storing that into m_UV chords, which, before someone points that out, I know perfectly well is not thread safe. Before we talk about multi-threading, we will address that issue. Okay, and yeah, that's it. So that's an example of the kind of changes that I've made to each object. Let's just look at a couple of others. Okay, so comb.cpp, this is basically the same, but I have also made some changes here to the actual maths. So I had previously used the std pow function, POW, to raise variables to a power, but simply we're just squaring them, so there's really no point doing that. So what I've done is replaced this with simply this v.getElement multiplied by itself, okay? Except v, we know, comes from BCK ray.mlab. We have to keep a copy of it here because we need it normalized for this to work. So what I've done now is this is, rather than a get element 0, that's now v.m_x multiplied by v.m_x, plus the same for y minus for z. Okay, and I think you can see how that's going to work. And then bckray.m.1, okay, and so on for the maths. Okay. I've also replaced this function here, replaced square root f with square root, which doesn't force everything to doubles. I believe, I could be wrong, but I think square root f static casts everything to double before doing the calculation, which could be slower. It probably isn't in our case because we're using doubles anyway, but it makes sense to use the square root function. And I've replaced the std pow usage there with simply b times b minus 4 times a times c. Pretty straightforward. Everything else pretty much the same. Some minor changes down here simply to use the new structures there. And yeah, I will go through and delete all the commented out code at some point, but that's all essentially the same. And then that's the calculation for the end cap. We talked about that in more detail when we talked about cones before, so go back and look at that episode if you want to know more. Okay, and cylinder.cpp is very much the same. Okay, so the same sorts of changes here to the maths. Got rid of the std pow functions and used the new element directly access the elements from the vector v. Okay, exactly the same, and the same there as well as we saw before. And that's all then basically the same. And modify things to use the new normals, the new vectors properly. Okay, so all of those changes, you know, as I was going through it, changing one, changing the other, they're all sort of gradually making the code run faster and faster and getting towards that 3.6 seconds result that we just saw. Okay, so the other place we've made changes is in Raymarch base. So here this stores vectors for the standard displacement in x, y, and z that we use for calculating the gradient of our distance function at a given point. So I simply replace those to instantiate QB-vector3s directly by passing 3 doubles to them, which we can now do. Okay. PointLight.cpp, the class for implementing our point lights for ray tracing. When we come to path tracing, these won't really be useful anymore, but you need it for ray tracing. So changes here, simply change everything to QB-vector3, and taking that into account of the proper usage of that. It's pretty straightforward, actually. That's it. Yeah, QB-vector3, double the dot product from that. And, oh yes, I changed the angle here from 1.57 something, I had it to m_pi divided by 2, and here as well, which is just simply for completeness. I think that generally makes things, it's just a bit better, a bit more accurate. Okay, probably more accuracy than we really need, but well, why not, if you can. Oh yes, and this change, of course, here in the constructor to define the default color uses the new direct instantiation of QB-vector3 rather than passing an std vector. Okay, and then we come to the base classes for textures and normals, and these are good examples of where we need to work with the new matrix class. So in texturebase.hpp, we initialize the transform matrix, obviously, to the identity matrix. We're instantiating QB matrix 33 now. We still do that by passing an std vector. Okay, I just figured that was easier than creating a constructor that accepted 9 inputs, or in the 16 in the case of QB matrix 44. And I think, because this isn't something we're going to do often, it only happens in the constructor when we set up the texture. It's not being called every time. I think really that's okay. Okay, in texturebase.cpp, not much change, but except here, where we initialize the rotation, scale, and translation matrices, we initialize them as 3 by 3 and then passed an std vector. Because we know they're QB matrix 33, we don't need the 3 by 3 now, so the new constructor doesn't accept that, so simply made those changes there. Nothing else is different. Everything else stays the same. Okay. Normalbase.hpp, exactly the same change. We initialize the transform matrix as you see there. That's exactly the same as we just saw for the texture class. And normalbase.cpp, again, pretty much exactly the same. We have a compute perturbation function. I've modified that to use the direct instantiation of QB-vector3, and also for the new up vector that we need there, and computing the direction, everything is now done on QB-vector3. That's all the same. We're using QB-vector2 here. This is why we needed it, for dealing with textures and normals. Okay. apply transform and so on. And the same here when we build the rotation scale and translation matrices, I've modified that to use the new constructor. Okay. Okay, so that's it. That's a really quick summary, quick run through of all the changes that I've made. We can just see that again. Let's just compile that and just see one last time how much faster that is than what we were dealing with before. And there we go. I barely have time to swipe the window over, and there we go, 3.6 seconds, which I think is actually pretty impressive. You know, wow. I mean, like I said, when I first started playing about with ray tracing, which was much longer ago than I care to mention, to render a scene like that at that resolution, this is 1280 by 720, I mean, that would have taken all day, or probably overnight on the computer I had in those days. So I think 3.6 seconds is really quite good. So I think we're getting towards the limits of what we can achieve now in terms of improving the performance. What I found is that playing around with it now, continuing to run through the profiler and iterate, is making smaller and smaller and smaller changes. So we're sort of getting diminishing returns now. I am quite happy with the performance now, and I think probably what I'm going to do is stick with it as it is. I think 3.6 seconds for that scene is still pretty good. When I run it with the path tracing algorithm that I'm working on separately, it is still really very slow. I mean, path tracing is slow in its naive form anyway, but yeah, you know, I still think we could probably do more improvement, but I don't really want to make that the focus of more videos. Otherwise, we're just going to go on forever making tiny and progressively tinier incremental improvements, which I don't think is going to be very interesting. So I think probably in terms of raw performance, we're going to leave it there. The next thing that I want to talk about is multi-threading. So the next video we're going to look at changing this to run as a tile-based renderer and look at some of the changes we need to make the code to make it ready for multi-threading. So we need to fix some of the issues that prevent it from being thread safe, which I have mentioned briefly as we've been going through it. So we will look at that in the next episode, and then the one after that we will look at actually doing the multi-threaded implementation. But you see, we're down to 3.6 seconds now. Just running in one thread. People who've been paying attention will notice that that is actually quicker than the 5 seconds I showed previously from my multi-threaded private version, and that is true, it is faster, because I've simply made more improvements to the code and implemented the new QB Vector 2, QB Vector 3, QB Vector 4 and QB Matrix 33 and QB Matrix 44 classes, which is, and then modifying the code to use those properly is then really what drives most of that difference. So when we come to do multi-threading, providing we get it right, in theory we should be able to get a lot faster than that. Now I have a 6-core, 12-thread CPU, so theoretically we should be able to push something like 10 times faster, which would bring this runtime down to about 300 milliseconds, 400 milliseconds, you know, for this scene, which would be amazing. Now, I don't think it will work quite as linearly as that. I don't think, I mean, certainly not with the multi-threading implementation I have right now. That's definitely not efficient enough for that. But I think probably if we can get around a 5 or 6-fold improvement, then that is going to be pretty good. So that's what we're aiming for. So there we go. That's really everything that I wanted to talk about today. I really hope that's been of interest. Apologies for rattling through it really quite quickly. There have been a lot of changes. I will push all the changes, of course, up to the GitHub repository, so you can simply look at the code there or clone the repository as you wish. And yes, as I say, next videos we're going to start looking at multi-threading, and then once we've covered that, we can move on to path tracing and other more interesting things. Okay, so as I say, that is everything I wanted to talk about today. I hope you've enjoyed it. I've had a great deal of pleasure making this video, and as always, if you have liked it, please do remember to hit that like button. It really does help with the YouTube algorithm, and if you haven't subscribed to my channel already, then please consider doing so. Hopefully you'll not want to miss the next videos on multi-threading. Okay, so thank you very much for watching. It's been a pleasure, and I really look forward to seeing you in the next video. Bye.